So here we have the differential equation x dot equals sine x, and that's defining the velocity of our solution functions x of t and at each point x. And we've plotted what this velocity looks like, sine x, as a function of x. And so the first thing I want to note is that if f at a point is equal to 0, then dx dt equals 0 at that point. This means the point is a fixed point. Is a fixed point. If a solution starts at that value, if a solution starts at a point x star where the velocity is 0, it's going to stay there for all time. And that means that not only the point is the point a fixed point, but that the solution x of t equals x star, recall that x star was a fixed point, is an equilibrium solution. That means it's a solution of the differential equation. If you plug in x of t equals x star, you'll find that it satisfies the differential equation at every single time point t. And it's an equilibrium solution because nothing's changing over time. So we call that an equilibrium. When we analyze this differential equation, we want to get some kind of qualitative picture of what all the different possible solutions of the differential equation are doing. And so we start with the equilibrium solutions. These are all the places where f intersects 0, where f is equal to 0. And so I'm going to draw lines there to represent each of the equilibrium solutions. There's an equilibrium solution when x is equal to 0, and there's another one when x is equal to pi, another one at x equals 2 pi, and one at negative pi. Of course, there's many more than these for the sine function, but these are the only ones that are visible given the graph we have above. So I've drawn in all the equilibrium solutions that I can see, and then we know that between 0 and pi, f of x is positive, and f of x is pretty small right near 0, and it's small again right near pi, and in between it gets kind of large, and that results in a solution curve that sort of looks approximately like this. And then we want to think about what's happening in between pi and 2 pi, and so things are negative there. The velocity is negative there, and that means the velocity is a little bit negative right near 2 pi and a little bit negative right near pi and gets quite negative in between. And so if we start up near 2 pi, our function is going to be decreasing all the way until near pi. And that looks like this. Okay. And then we have kind of 3 more spots to look at between 0 and negative pi, below negative pi, and above 2 pi. Let's start with above 2 pi. Above 2 pi, our function gets positive. We don't know what's happening after kind of a small distance above 2 pi, so we're only going to draw in a little bit of what might be happening. The same thing is true below negative pi. We just don't have that much of the function, but we know that it's increasing down there, so right near this equilibrium solution, it's increasing from below. And now we just want to fill in what's happening in here. Okay, well, it's decreasing throughout this range, so that means if we start somewhere a little bit below 0, we'll be decreasing for a while. And that looks like this. Note that when the velocity is small, the slopes are small, and when the velocity is larger, the slopes are large, and so we go from small velocity to bigger velocity to small velocity again, and that corresponds to sort of going through this curve where we start near 0, we're a bit away from 0, and then we come back near 0. And from this kind of picture, now it's very clear that this is a stable equilibrium. What do we mean by stable? We mean that nearby trajectories are attracted to it. This one is unstable, stable, unstable. As a rhetorical question, I'm going to ask you right now, will these always alternate? And I'm going to put in the stability markings we use. When something's stable, we draw a solid dot. When something's unstable, we draw an open dot. Now I want to look more closely at our two most common types of zero crossings. So we have the velocity plotted as a function of x, and here we have the velocity start negative, increase through 0, and become positive. And this corresponds to a fixed point. In this case, x is basically 0 at this fixed point, and that's an equilibrium solution, and we're going to draw that in over here. Okay, so over here we have this equilibrium solution where x is equal to 0 for all time is a solution of our differential equation, and we can tell that's a solution because if we plug in x equals 0, then x dot is also equal to 0, and so things never change. And now we ask what happens if we were to start just at an x just a little bit above 0, and we can see that the velocity is positive when we're just a little bit above 0, and so x will increase. And then the velocity is even more positive, so x will increase faster. And then the velocity is even more positive, so x will increase even faster. So we're going to draw that in. We're starting at a point that's a little bit below x at some time that's negative, and we're increasing faster and faster and faster. And now we're going to look at what happens if we start at an x a little below 0. So now our velocity is negative, so we go more negative. And now our velocity is even more negative, so we go yet more negative, and our velocity is yet more negative. And so we start down here at some time before 0, and we move away. And this motion is exponential. We have exponential growth away from the equilibrium and exponential decay away from the equilibrium. And that's true for the whole region where this remains linear. Okay, and so this slope, where we went from a negative value to 0 to a positive value, the slope of this line is positive, and that positive slope corresponds to an unstable fixed point. Okay, so this is an unstable fixed point, and that corresponds to the slope, df dx, being positive. Okay, then what about when the slope is negative? Well, we've again drawn it so that 0 is an equilibrium solution, is a fixed point, so I'll draw in that equilibrium solution. And now we look a little bit above 0. Now if we go a little bit above 0, our velocity is negative, so we actually get closer to 0. And our velocity is negative, but even slower, and we get closer to 0. But we're getting close to 0 very, very, very slowly. So let's go a little further away. Our velocity is negative and relatively big, negative and getting smaller, negative and getting smaller, negative and getting smaller. So actually we're going to approach 0 in an exponential way, meaning we're never going to reach it, but we're approaching 0 from above. And let's check out what happens if we start with a negative x. Well, now we're increasing because our velocity is positive, and we're still increasing. Our velocity is positive but slower. Still increasing, velocity is positive but slower. Still increasing, velocity is positive and yet slower. So it looks something like this. And this is a stable equilibrium, and it's corresponding to this negative slope. So when the slope is negative, we start positive, we go through the fixed point, and then we become negative, and that leads to increasing towards the fixed point from below and decreasing towards the fixed point from above. And so that is df dx is less than 0. And now I want to look at a bunch of more unusual cases. So the most common case we're going to encounter is that we either have a line going upward or a line coming downward, and that results in either a stable or unstable fixed point. But there are some more unusual cases, and I'm just going to run through them. Let's say we have something that's shaped like a quadratic, and it happens to just be touching the axis, intersecting in exactly a single point. So there's exactly a single fixed point, resulting in an equilibrium solution right at 0. But in this case, what's happening below 0? Well, we're increasing. And I'm going to note that as we get really close, things are actually slower than linear. Things are increasing quadratically slowly, very, very slowly as we approach 0. And then what happens when we're above? Again, things are moving very, very slowly, but they're moving in a positive direction. And so we're increasing both above and below, and that means that from below, we're approaching the equilibrium solution. From below, we act like we're stable, but from above, we're acting like we're unstable. We're going to call this case half stable, and we're going to draw in a circle, and we're going to fill in the correct half of it. So that circle is representing our fixed point, and this is a half stable situation. And if we go to the next graph, this is also going to produce a half stable situation. This time, we're going to be moving in a negative direction, both above and below the fixed point. So that looks like this. Okay, and so it's half stable, but the half stable side is a different side. I'm drawing this really big, not because it should be drawn really big, but just because it's hard to draw for me right now. And now we're going to go to these final two cases. So this case is quite a bit like the line in that we have one sign on one side of a fixed point and a different sign on the other side of the fixed point. We're just not going through in a linear way. And so we still have this equilibrium solution in both cases. And we're increasing when x is negative, and we're decreasing when x is positive. So x is negative, we're increasing. X is positive, we're decreasing. This is a stable fixed point. The trajectories don't converge to it as quickly as they would if we had a straight line, but it's still stable. And this bottom one, positive x moves away, negative x also moves away, and so this is unstable. And so we draw that with an open circle. So when we think about the general case, we have some function, f of x. We have a graph of it. The fixed points occur wherever that function happens to pass through 0. And then to figure out the stability of those fixed points, we look very close to the fixed point and we ask, okay, is the line sloped this way? Is the line sloped this way? Is it a quadratic? And we can draw in some arrows. When we're below, we can see that we're increasing. And if we move into this regime over here, we're also increasing. And if we move into this regime over here, we can see that we're decreasing. So we can draw in arrows of this type along the axis that tell us what sign f of x has at particular points. And those arrows can help us to see the stability. We can see that this point is half stable, with the stable side being below, and that this point is stable because trajectories are flowing towards it from both sides.